Okay, today we will discuss about practical laser diodes, that is practical device, how the device looks like, what kind of packages and what kind of specifications. If we see a typical data sheet or a specification sheet, do we understand what the parameters stand for? And we will also discuss about handling issues. There are some safety related issues, safety to the device as well as safety to the user, and these issues we will discuss. So, practical devices. So, devices. So, in devices I would like to discuss about device specifications. So, practical devices. Practical device specifications and device packages, what kind of packages are used, and in handling there are two issues, which is safety of the device and safety of the user. Safety of the device and safety of the user. Let us start first with the device specifications. So, let me keep a typical laser device specification. It is a little big slide there, but I hope you can see that. Okay, let us first see specifications one by one. This is specifications at T is equal to 25 degree C. It is a pigtailed laser diode, fiber pigtailed laser diode. What it means I will show you in a minute, fiber pigtailed laser diode. So, the first parameter which is written, threshold current here, I threshold, test condition CW, CW standing for continuous wave mode of operation. A laser can be operated in CW mode, CW standing for continuous wave, and pulsed. So, two modes of operation for all laser diodes, CW continuous wave and pulsed. So, CW means if you plot with time versus power. So, P out if you plot, you will have a certain level fixed, that is CW continuous wave. And if you for pulsed laser, if you plot time versus power P out, then you will have power varying and so on. So, that is a pulsed output, P out versus time. So, CW and pulsed. So, the threshold current, typical parameter, you can see that it is 25 milliampere, CW units are given 25 milliampere, minimum is 10, maximum is 40, because there could be some variations in the device. Therefore, usually they specify minimum and maximum. Forward current, that is the operating current IF for CW, to get 1 milliwatt power, P output 1 milliwatt, you pass a current of 40 milliampere. At 40 milliampere, if 25 milliampere is the threshold current, that is when power output starts, then at what has been shown there is this. So, we recall the characteristics that we have, IF, forward current versus P out, and we have almost 0 output and then output going like this. So, this is the threshold value. So, in this particular example 25 mA is here, and when the output is, when the current is 40 mA here, 40 mA, output is 1 milliwatt. So, we understand this. and to get 1 milliwatt you may require sometimes 75 mA, because there may be some device degradation, but typically about 40 milliampere. Forward voltage, the voltage, because it is a forward diode and therefore it is a diode, forward bias diode, forward voltage is 1.2 volt. Wavelength, there are 1300 nanometer wavelengths, 1550 nanometer wavelengths. So, 1300 nanometer typical wavelength is here, minima and maxima, that is plus minus 20. It does not mean a particular device will give that. A particular device, when maintained at a particular temperature and current, will give a fixed power output and a fixed wavelength. But in a lot, that is in a batch of several devices, some devices may have slightly varying characteristics. That is what they mean by minimum and maximum. So, fiber output power, this is 1550 nanometer CW, and this is the typical output. And fiber output power for a DFB laser, DFB here, we are familiar with DFB now, distributed feedback. The forward current at a forward current of I threshold plus 35 milliampere, you have an output of 4 milliwatt is the output. And the spectral width of the DFB, so we know now DFB laser, distributed feedback. So, I am discussing this. So, let me erase the remaining ones. A DFB laser, the spectral width, as you can see, the spectral width for the DFB and Fabry-Perot are very different. Distributed feedback laser, the output is output of a distributed feedback laser. If you recall that you have some side lobes. So, what I have plotted is frequency nu or wavelength lambda. Normally in light we discuss in terms of wavelength. So, wavelength lambda here versus the power output. So, P out. So, this is full width at half maximum. So, whatever is the full, so the width at half maximum is delta lambda here. So, delta lambda or delta nu. And this is the center wavelength, lambda c or lambda 0, the center wavelength of the DFB. These are the power. So, typical power, if you see here, that this may be 3 dB, 0 dB, so 3 dBm. So, 3 dBm. So, this is 0, this is minus 10, minus 20, minus 30, dBm. dBm, I hope you know the definition of dBm. 1 dBm is, so 0 dBm here refers to, implies 1 milliwatt. The power in dB, those of you are not familiar, power in dBm is defined as 10 log P here in milliwatts. So, P in watts here divided by, with respect to, so P1 by P2, whatever is P1 by P2. So, here 10 log P1 by P2 here. P2 is reference, and therefore, so P2 is reference to 1 milliwatt. Please see, if this is the actual output, power output. So, P1 by P, this is the definition in general, but definition of dBm is, so P out actual power with respect to P2 here, that is equal to 1 milliwatt. What it means is, if the output power is 10 milliwatt, those of you are not familiar, if the output power is 10 milliwatt, then if in the denominator is 1 milliwatt, this ratio is 10. So, log 10 is 1. So, multiplied by 10. So, this is 10 dBm equal to 10 dBm. So, 10 milliwatt power is equal to 10 dBm. If the output power is 1 milliwatt, so if you substitute 1, here this is 1, log 1 is 0, so 0 dBm. So, 0 dBm is 1 milliwatt, and so on. Please, those of you who are not familiar, put some numbers and be familiar with it. So, the fiber output here, is, in this case it is given in milliwatt. So, 4 milliwatt. The spectral width delta lambda is given here for CW at 1 milliwatt power is 0.1 nanometer. Delta lambda is 0.1 nanometer. If you look at Fabry-Perot lasers, normal Fabry-Perot lasers, it is about 2 to 3 nanometers. This being a DFB laser, the spectral line width is very narrow. Then you see the side mode suppression ratio. I have discussed about this for a DFB SMSR at CW output of 1 milliwatt, the SMSR is 20 dB. 20 dB is the ratio of this power to this power. In my diagram, for example, this is 3 dBm and this is minus 20. Therefore, what is the SMSR? So, SMSR is equal to 23 dB. In my diagram, it is 23 dB. Output is 3 dBm. 3 dBm, those who are not familiar, is 2 milliwatt. 2 milliwatt is 3 dBm. You put here log of 2 milliwatt by 1 milliwatt, log 2. Log 2, if you know the number, it is 0.3010 multiplied by 10 is 3.01, which is 3 dBm. All right. So, 3 dBm is 2 milliwatt here, and the power in the side lobe is minus 20 dBm. So, the difference is 23 dB. This is a ratio. So, please see it is dB, not dBm. SMSR is the ratio. So, it is in dB. If you go further, the spectral width for a Fabry-Perot is given here 3 nanometer. Just now I mentioned, for a Fabry-Perot laser, the spectral width is delta lambda equal to 3 nanometer. So, typically 2 to 3 nanometer is for a Fabry-Perot, and 0.1 or less. The current DFB lasers have even much less than 0.1 nanometer as the line width. The next one is monitor current. You see there is a parameter written monitor current at Vm equal to 0 volt, that is monitor voltage equal to 0, output power equal to 1 milliwatt, the monitor current is 0.5 milliampere. I will discuss this in a minute. So, let me finish the remaining parameters here. Thermistor resistance, there is a thermistor here, and the resistance of the thermistor is given 1 kilo ohm typical, and thermistor temperature coefficient of resistance. These two are required to maintain the temperature of the device. I will discuss in a minute, but you can see thermistor temperature coefficient of resistance is -4% per degree centigrade, which means as temperature increases, thermistor resistance decreases. It is -4% of the resistance. If originally if it was 100 ohms of the thermistor, then 1 degree increasing is -4%, that is it will come down to 96 ohms. So, the temperature is changing, the resistance is changing with temperature. So, that is the temperature coefficient of resistance, and this is TEC power, the thermoelectric cooler power. All laser diodes are operated with a temperature controller, and it is a TEC, that is thermoelectric cooler. The power taken by the cooler is typically about 2 watts. So, this is a sheet of specifications. So, now when we look at the specifications, the only thing that I have not discussed so far is the monitor photodiode and the thermistor. We will come to this in a minute. All right. Let me show let me discuss the packages, and then I will come to this monitor photodiode. All right. Maybe I will first discuss the monitor photodiode, because when we go to packages also you will see that there are leads which are connected to thermistors and monitor photodiode. So, it is better to discuss the monitor photodiode right away. So, if we see a typical data sheet, and if we understand all the parameters, technical parameters of a device, it means that we have reasonably understood the device and its operation. Otherwise, it simply means we know only the theory, we have no idea about what is it in practice. Okay. So, let me take device package, the thermistor. You see here the monitor photodiode. What is this monitor photodiode? a typical Fabry-Perot laser or DFB laser. So, you have I have shown only the active region and other layers are understood. So, I am not showing it again. This is our active region and the current is flowing here and output is coming. Output is coming from here. Please see, these are cleaved facets, 32% reflection both the sides. So, obviously output will come from both directions. Output comes from both the directions in a laser diode. In fact, the early laser diodes in the specification, it used to be, today it does not say, it simply says output power. In the early laser diodes, it was always specified P out equal to 2 milliwatt per facet. In the 1970s and 80s, the power was specified per facet. Facet means per phase, which means 2 milliwatts comes from here and 2 milliwatts come from here, two directions. But in any application, we need light coming from one direction. You do not imagine a torchlight where light is coming from in front and behind. So, you want light to come from one direction normally, and therefore, but in a normal device light will come from both the directions unless you coat this with a mirror, which is a difficult proposition, expensive proposition, and therefore, what has been done is this output is incident on a photodetector. So, I am showing this photodetector as a diode here, which is actually integrated with the chip, but I am showing it as separate. The output is incident on a photodetector. The photodetector will generate a reverse current IP. What is the advantage? By measuring this current IP, this IP is proportional to incident power. The IP, the photocurrent, reverse photocurrent is proportional to P optical power incident on it. And therefore, by measuring this IP, we can find out what is the power which is coming. We can calibrate it and then we know simply by measuring the current, we know what is the output power. What is the advantage? The output power coming from the other side is the same as the output power which is coming here. So, if you know this, you know the output. Without disturbing the output, when a laser is on, you know what is the output power. So, today's laser drivers will have an output here and there is a display here. So, display. In the display there are several parameters which comes, but it also tells you what is the P out. How will it say what is the P out? Because output is coming from here. Without measuring this P out, how does it say this P out? It is saying this P out by measuring the power coming from the other end. So, monitor photodiode and the monitor current is very important measure for the device. Why? If you want to maintain the power constant, many applications require that the output power P out should remain constant. If you monitor the photocurrent here, you can find out what is the power which is coming. If the monitor current starts dropping, it tells you that the output is dropping even without measuring separately what is the output coming from here. So, the output power is constant if the monitor current is constant. So, this monitor current is independent of the output which is coming from the device. So, by monitoring this current, you can find out what is the output. It is not just finding out the output. If the power starts falling down, the current starts dropping here, then there is a feedback which is given so that this current I is increased so that the output again is jacked up. When the power starts dropping, the monitor current drops. That is why it is called monitor photodiode and monitor current. This is monitoring continuously, and as the current drops, for whatever reason, if the output goes down, you can increase the forward current or the bias current through the diode and raise it back so that the output power remains a constant. This is very important in the case of constant output power devices, the monitor current is the one which gives you the difference signal, so that by maintaining that the difference signal constant, you can maintain the output power constant. So, that is the monitor photodiode. So, this photodiode is integrated with the laser chip, and there are terminals provided for the monitor photodiode, separate terminals. When I talk about the device package, I will show you that there are terminals provided for this photodiode, so that you can also take out the current for some other external circuit which will maintain that current, which will maintain the power output constant by measuring the difference signal or the change in the monitor current. So, this is the monitor photodiode. The second thing that we encountered is thermistor. The thermistor is a temperature dependent resistor. Thermistor is nothing but a temperature dependent resistor with a temperature coefficient of resistance. It is a temperature dependent resistance, which means if you change the temperature, the resistance changes, and this thermistor is also integrated along with the laser chip in the same chip, so that if the temperature of the chip changes, that means if the temperature of the laser diode changes, there will be a change in this resistor. The change in resistance can be used as a difference signal again to the thermoelectric cooler TEC, thermoelectric cooler. The change in resistance of the thermistor can be used to power the thermoelectric cooler. What is the thermoelectric cooler? The Peltier cooler, where by passing a current you can change the temperature between two junctions. The two junctions sitting at two different temperatures will give rise to a voltage signal, and by changing the current you can change the voltage, or by changing the voltage you can change the temperature. So, this TEC is a thermoelectric cooler based on the junctions, and the current to this TEC, the TEC was consuming about 1 watt power. The current to this TEC can be controlled by this resistor, temperature dependent resistor. So, if the temperature of the chip changes, the resistance changes, and therefore, that temperature coefficient, there was a parameter TCR which was -4% per degree centigrade, which means if the temperature changes through 1 degree, the resistance changes by -4%, that is, it decreases. All these thermistors are basically photoconductors. If you increase the temperature, the resistance drops because more number of carriers are generated, thermally generated carriers, and therefore resistance drops. That is why you see here minus, there is a -4%. So, that controls the current which goes to the TEC, and TEC can again pass more current and make it cooler, so that the temperature is maintained. So, both the thermistor and the monitor photodiode are to maintain constant temperature and constant power output of the device. Okay. So, we have seen now all the specifications here. So, let me remove this and we go to the device packages. So, we understand now all the specifications which are there. There are some more specifications in data sheets of certain manufacturers. I would not go into those details. These are the basic things which are there in general in almost all lasers, all laser diodes. There may be specific parameters relevant to specific devices in addition. So, let us look at device packages, and then we will go to handling. So, device packages. All the packages, either they give free space output. So, free space output, packages which give free space output or packages which have fiber pigtail. Almost all the laser diodes used in communication are fiber pigtailed laser diodes, because you can directly splice it to the fiber which is on the line. Fiber pigtail or free space output. The fiber pigtail output, there are two specific packages here. One is called the 14 pin DIL, dual inline, or sometimes DIP, 14 pin DIL package, usually for low power applications, and for high power applications it is invariably 14 pin butterfly package. I will show you these. I have brought a butterfly package, but DIL I will show you. This is just like an IC, a typical IC. The free space output here, there are two common packages which are used. One is called the TO3 window can. So, TO3 window can package, and the other one is SOT 148 window can. So, four types of packages which you see in common. So, first let me show the TO3 window type package. So, TO3, find out what are the, it may be interesting to find out what are the abbreviations standing for. You find out what are these TO3 and SOT 140. So, the TO3 package looks like a typical power transistor. Those of you who have seen power transistor, it looks almost the same shape. I hope you have seen a power transistor. This is the top view. There are two holes here to mount the power transistor. These are slots to mount the, this is the top elevated, this one, and the bottom view looks like this. Typically 8 pin, these are 8 pin devices. This is the bottom view. So, top view and bottom. The pins start from 1 from here, 1, 2, of course these are all provided in the data sheet, and 8 comes here. It is usually in a clockwise direction when you look from the bottom, 1, 2, 3, 4, 8. This is the top, and at the top there is always a window. So, this is a glass window. So, here is glass window. Why do we need a glass window? Because light has to come out. So, light comes out from here in this direction. So, this is the light comes out perpendicular to the board. There is a glass window. Otherwise, it looks, if the glass window was not there, it will look just like power transistor. So, there is a glass window from which light comes out like this. I will show you the next one, SOT 148, because I also have those SOT 148 packages. So, so this is SOT 148. This looks like this. The top, it is circular. The top view is this with a window. If we place these transistors, the electronic transistors, diodes, and optoelectronic components like laser diodes, there is no difference except that there will always be a glass window on top, because light has to come out from a source, and for a photodetector light has to be incident. Otherwise, they look like just the can of a transistor, that familiar device. So, I will show you in a minute. So, this is the top, and from the bottom there are different 4 pin devices, 3 pin devices. So, usually there is a cut provided which will tell you that this starts with 1, 2 and 3 also, but others will not have an opportunity to see this. So, it is more important for the others, but nevertheless JOP people also can come. You come at 12 o'clock if you are free. After 12? So, just after 11 to 12 class you come. Okay. All right, let us continue. So, this is the top view and this is the glass window as before. So, here is the glass window and this is the bottom view here. So, I will show the packages. So, you can see the packages here. We are not supposed to touch those, but there are 1 or 2 things. What I have kept along with this is a normal LED here, an LED which is 2 pin diode, light emitting diode, and this is a spoilt one. So, I can touch that, but it is important that you see that there are 3 terminals there. There are 3 terminals and these are the same 3 terminals here, 1, 2, 3, and that is the bottom view. And the top view, as you can see, there is a glass window in each one of the devices. This is a laser diode used in CD writing device, and from the this gives an output power of about 20 milliwatts. This small device gives power of about 20 milliwatts. There are 3 terminals. They are, it's like this. The first one is 1, okay, let me write 1, laser diode anode, laser diode anode. 2 is common ground, ground, that is case ground, ground plus cathode of laser diode and monitor photodiode, MPD. I am writing MPD, monitor photodiode, cathodes of LD and MPD, and 3 is the anode of monitor photodiode. I will show a schematic how it looks like. Where can I show? All right, because next we will discuss the so it looks like this. It is a 3 terminal device. So, this is 1, the laser diode, terminal 1. This is terminal 2, which is actually grounded to case ground. So, this is case ground, and here at terminal 3 we have the monitor photodiode. So, anode of, so this is 1, 2, 3. This 1, 2, 3 I have now shown is 1, 2, 1, 2, 3. 2 is, so it is a common cathode here. This is the monitor photodiode. So, this is the photodetector MPD and this is the laser diode. So, the 3 terminals that you see on the device here, the 3 terminals are, I hope you can see all the 3 terminals, and let me, yeah, this is a used one, it is a defective one. So, you can see that that is now not really the is a good view, because you will not see the lead if I completely keep it. It is sitting in that slot. All right, let me, but do not touch the device. Why you should not touch, I will discuss in a minute. So, this is the SOT 148 package, typical laser diode. If we give you there is a another small laser diode here, it is a low power one, and let me take it out, and you can see this is just like a transistor. There are 3 terminals, it is like a transistor, except that at the top there is a glass window. In a transistor you simply have the metal can, there is no window. Here in every optoelectronic device there will be a window at the top. Let me go next to the other 2 packages, because we have to wind it up, and very important are the DIL and butterfly package. Again I have brought a butterfly package to show you. This is also a used one, a defective one, otherwise cannot touch these. Let me take this out and show you the butterfly package, and you will know why it is called a butterfly package. It is a fiber pigtailed device. This is a fiber pigtailed butterfly package. I hope you can see it. So, what you have is a 14-pin device. You can see 7 pins here, 7 pins on the other side, and fiber is coming out. So, this is already pigtailed to a fiber, and this is the connectorized output of the fiber, because in all fiber optoelectronic instrumentation you need connectorized output, and therefore, this is the fiber end is connectorized. And here is the butterfly device. It is called butterfly because butterfly when opens its wings, it looks like it looks like these look like wings of the butterfly, hence the name butterfly. And fiber pigtailed, fiber is already pigtailed here. Pigtailed means if you have the device which is coming out here, so there is the device coming up, the light which is coming out here, then the fiber, there may be a micro lens. Usually there are different techniques of coupling light into the fiber. The fiber end is, there is a micro lens made at the end of the fiber. This is the optical fiber. A micro lens is micro lens. The fiber end is made in the shape of a micro lens, so that the light which is coming out of the diode is immediately coupled into the fiber core. So, and the whole thing is sealed, so that there is no relative displacement. It is already completely ready and the fiber is coming out from here. So, this is called fiber pigtail. Fiber pigtail laser diode is a device where the fiber is already aligned, pre-aligned and hermetically sealed. It is pre-aligned and sealed in the package. So, this has 14 pins. I will show you another diagram. This is a very nice device because you can see its bottom. It can be mounted with 4 screws on a heat sink, and it has a very good contact with the heat sink. The bottom, its belly, this is its belly. The bottom is in good contact with the heat sink, and that helps in maintaining the temperature. So, you can mount it with the 4 screws here at the 4 corners and gives very good contact with the heat sink. I will show a diagram of the 14-pin DIL package or DIP. So, here is the, it looks like an IC. At the back there is a connector or a connecting plate which is again for providing heat sink. So, this is for heat sink here. I hope the diagram is clear. This is schematic, and you can see the fiber connector and fiber pigtail. And here also the pin diagrams are shown. You can again see what the pins stand for: monitor photodiode negative, monitor photodiode positive. Here is the monitor photodiode. The laser diode positive, anode and cathode. The thermistor, there is a thermistor shown here, thermistor. NC standing for not connected. Although there are 14 pins, all pins are not connected. So, NC standing for not connected, and the top 2 electrodes are for the TEC. So, this is the pin diagram, and if you see this, if you understand what is there in a practical device, I hope you know how the device looks like. So, this is a 14 pin DIP package. Let me very quickly come to the laser handling, safety to the device and safety to the user. Very briefly, safety is a very big topic. So, laser handling. Safety of the device and safety of the user. Every user is supposed to be aware of the safety, laser safety aspects. In fact, these are mandatory by law, that those who use laser diodes or lasers in general must know the safety aspects. So, let me first discuss the safety of the user. The safety of the user is of course because of the power output of the laser, the damage that the laser output can cause. The damage is primarily because it is a highly monochromatic coherent radiation, can be focused to very small spot sizes, and therefore, the intensity at the focused spot can be very large and can cause burns, and if it is incident on the eyes, then eyes can get damaged, and therefore, lasers are classified based on the output power. Classification of lasers based on output power. These are called class 1, class 2, class 3. Class 3 has usually two subclasses, class 3A, class 3B. This is true for all lasers, not just semiconductor lasers, and class 4 lasers. Class 4 here. Actual classification will also depend on what is the wavelength of emission, but typical approximate range of powers, class 1, the power is typically few microwatts P output. So, this is P out, few microwatts to few tens of microwatts. Few microwatt to few tens of microwatt. These are safe lasers. Safe lasers. Most of these are used at the research level, and there are materials which give very small amount of power, and few class 1 laser. Class 2 here stands for powers less than, anywhere but less than 1 milliwatt, P out less than 1 milliwatt. Reasonably safe, but avoid direct exposure, to the eyes, means if the laser beam goes directly into the eyes, it could damage the eye. So, avoid, otherwise with the reasonable precautions you can handle these lasers without going to special safety measures, but take care to avoid direct exposure to eye or metallic reflections from metals which are as good as high reflection entering your eye. Class 3A here stands for typically 1 milliwatt to 10 milliwatt. Class 3A, and class 3B is typically 10 milliwatt to 100 milliwatt. Please let me make it clear that the numbers are vary with the wavelength and the damage that a particular laser can cause. But these are the approximate power ranges. Most of the lasers which we handle in applications other than maybe in nonlinear optics experiments or in industrial applications, we handle class 3A and class 3B lasers. In most of our laboratories, communication applications, the power involved are here, class 3A and class 3B. So, class 3A and 3B here, eyewear is a must, laser goggles. So, laser goggles, wear laser goggles or laser safety wear. So, laser goggles plus avoid direct exposure on body parts. Avoid direct exposure on your hands, body parts. They could be harmful to the skin. But laser goggles is a must. You must use laser goggles when you are handling class 3 lasers, because they are definitely harmful to the eyes. The scattering, the amount of scattering that could come or reflections which could enter your eye could be large enough to damage your retina. Again, as I said, it will depend on the ocular transmission. There is something called ocular transmission. Ocular transmission. Ocular transmission is the fraction of energy transmitted from the eye lens to the retina. The energy transmitted from the lens of the eye, if you, all right, let me, so this is your eye, all right, or my eye. So, the retina is here, at the back, and this is the lens, eye lens. So, the fraction of energy transmitted, so light is incident from here, this is the cornea and the eye lens, the dimensions are not all right, just to, so the light which is incident on the retina here, so retina is at the back, the fraction of light which is incident is called ocular transmission. So, the ocular transmission is very high for visible, almost 95% in the visible region, that is approximately 0.6, so around 0.6, 0.5, 0.6 micrometer, 0.5 to 0.6 micrometer, whereas this is about 0.1% at 1550 nanometer or 1500 nanometer. Fortunately for optical communication people, this is the fraction of light which is incident on the retina is much smaller, and therefore, most of the light is absorbed here in between. That is actually over a wide region, and therefore, it is not so harmful, but here at the focused spot, the amount of light incidence is only 0.1% at 1550. In fact, those who work with the defense, they call it as eye safe laser. 1.5 micrometer is called eye safe laser. So, 1.5, so eye safe wavelength. There are many places they need to use lasers for aligning or for range finding. So, you would like to use lasers, but they should not harm the eye, and therefore, they tend to use the eye safe laser wavelength. To mark targets, they have to use lasers, and usually it is around 1.5 micrometer, because they are relatively harm free. Class 4 laser, let me come to class 4 laser. It is mandatory to wear laser goggles, and definitely you need to, so power P out greater than few hundred milliwatts, depends on the laser. As I said, you see the ocular transmission is different. Similarly, the transmission through the skin, the absorption of body skin depends on the wavelength, and therefore, exactly you cannot specify numbers, but few hundred milliwatts, several watts, the Nd:YAG laser which we use in the lab, several watts power, you must wear all the safety goggles, safety wear, and it is necessary to use interlocking system for the laser lab, that is interlocking plus interlocking arrangement. What is this interlocking that I am referring to? That is, you are working in a laser lab, there has to be a red light, blinking red light. If the laser is on, there has to be a red light which is blinking. Such class 4 lasers, these are requirements by law, that there has to be a red light blinking, and which means any user or anyone, any visitor cannot enter that lab when the red light is blinking. By chance, by mistake, if he opens the door, if he or she opens the door, the laser would automatically shut down. There is an interlock with that. You open the door and the laser will shut down there automatically. So, that is called interlocking arrangement. So, this is also mandatory by law. For some reason, if the interlocking is not working, sometimes it happens in our lab, then we bolt the room from inside, so that nobody by mistake enters. So, someone has to knock and wait there, and then you will switch off the laser or put the shutter on and then open the door. So, this is the safety measures depending on the classification of lasers. So, safety of the user. Last point, safety of the device. I hope we have couple of minutes. Safety of the device. I will stop here. All these high speed devices are sensitive to ESD, electrostatic discharge. ESD, electrostatic discharge. Maybe we will discuss it in some other class because we do not have time, but all high speed devices including CMOS devices, you may be knowing that they are static sensitive. So, the environment has to be static free, you have to use grounded mats, the user has to wear, you have to wear grounded straps and the wire has to go to a central node where it is grounded. It is grounded means you are not directly grounded, grounded through a 1 megohm resistance. Please remember, there has to be a 1 megohm resistance, otherwise you will be a ground, and by chance if there is a short circuit, it will just all the current will go through you, and therefore, it goes through a 1 megohm resistance. Okay. So, this is these are straps which need to be worn, and I will show it here for those of you who are not able to see. It is a metallic strap with a pin, and that goes to a point where you are grounded. Grounded means there is a ground path provided, so that any static charge which is there in the environment, which is on your body, does not pass through the device. You please see the basic idea. What is current? I is dq by dt. Current is dq by dt. If the charge passes through in a very short time, current will be very large. That is the whole idea about ESD. There are some charges which are on your body or on the work table, and when you touch the device, the charge will pass through the device. Because the device is very fast, dt will be very small. It will pass through at a very fast time, and therefore, if you put here nanosecond and this charge may be very small, the current will become very large, and therefore, this ESD problem is only with high speed devices, including electronic devices as CMOS devices, very high speed devices. This is very, very important for laser diodes, otherwise you are bound to damage the laser diodes. So, I will stop here. More details you can see from the literature. This is basically to give you an idea about the various practical issues, practical aspects of the devices.